The Vethkai ship was leaking plasma at a rate I calculated would kill its crew in about 90 minutes, which gave me 89 minutes to figure out what a Vethkai engine even was. Let me back up. My name is Dara Ruiz, and I run Waystation Kaleo, which is a fancy way of saying I'm the only certified mechanic within 11 light years who will look at your broken ship and not just hand you a parts catalog. We get everything through here. Tarathi cargo haulers with seized grav plates. Henny survey vessels with cracked heat exchangers. Once, memorably, a Quareth battle cruiser whose captain insisted the problem was spiritual misalignment, and not, as I correctly identified, a coolant line installed backwards by someone who'd clearly never read the manual. I fixed it. They gave me a ceremonial dagger. I use it to pry open junction boxes. The point is, I fix things. That is the entire point of Waystation Kaleo. The Vethkai had apparently not received the memo about what a repair station was for. The ship, a diplomatic courier, sleek and crystalline in the way all Vethkai engineering is, like someone had taught geometry to grow, limped into my dock at 3:40 station time, trailing a very pretty, very alarming ribbon of ionized plasma. The docking clamps engaged. The plasma ribbon kept going for another 3 seconds after the ship stopped moving, which is not a great sign. The commander came through the airlock before I'd even finished pulling up my diagnostic tablet. Vethkai are tall, silicon-framed, their movements precise in the way that crystals are precise, no wasted motion, everything angular and intentional. This one's designation translated roughly to Vessel Commander Eichsthal, and Eichsthal was radiating the equivalent of contained panic, which mostly looked like their facets vibrating at a slightly higher frequency than usual. Human repair station, Eichsthal said. Their translator rendered the words in flat, careful standard. We require a replacement resonance crystal primary drive class Vethkai configuration 7-4. Immediately. I pulled up my inventory. I didn't need to, I know my inventory, but I did it anyway, because sometimes people need to see you looking before they believe the answer. I don't have one, I said. Then you must obtain one. Nearest Vethkai supply depot is 43 light-years away. At your ship's current plasma bleed rate, I checked my tablet, did the math in my head. You have about 86 minutes before your secondary containment fails, and your crew has a significantly worse problem than being late to wherever you're going. Eichsthal's facets vibrated harder. Then we are finished. That word finished, I'd look it up later. In Vethkai, it was a technical designation, a thing that had reached the end of its functional period and was to be archived, like a file you close, like a door you lock. I looked past Eichsthal at the ship, plasma still wisping off the starboard nacelle in faint luminous threads. Can I see the crystal? I asked. There was a pause that I would later understand was profound. You wish to examine a failed component. I wish to see what I'm working with, yeah. Another pause, then, the crystal is failed, examination is unnecessary, replacement is the protocol. I don't have a replacement, so examination is what I've got. I grabbed my toolkit, real toolkit, the one with the beat-up latches and the thermal probe I've recalibrated 14 times, and walked toward the ship. You can come with me or wait here, but either way I'm going to go look at it. Eichsthal followed me. I could feel the frequency of their discomfort like a low hum in my back teeth. The crystal was in the engine core, which was accessible through a maintenance hatch that I had to ask Eichsthal twice to show me how to open, because Vethkai fasteners do not work on any principle I've ever encountered. It looked like someone had taken a very large, very perfect hexagonal prism of pale violet glass and dropped it from a significant height. The fracture ran diagonally across roughly 40% of the structure. A clean shear line with microfissure, branching spreading another 15% in either direction. I got out my measurement probe. Structural integrity, 23%. Plasma bleed confirmed through 17 distinct microfissure outlets along the lower third. Okay, I said, here's what I know about resonance crystals. You know nothing about Vethkai. I know that a crystalline resonance drive works by sustaining a standing wave pattern inside the lattice matrix, which gets disrupted if the lattice loses structural coherence. I know the plasma bleed is a symptom of wave energy escaping through the fissures rather than cycling through the drive system. And I know that if I can brace this fracture well enough to hold the lattice together at the critical resonance points. I was already pulling components out of my toolkit, scanning the maintenance bay for salvageable materials. We don't actually need a replacement. We need a repair. Eichsthal was silent for a moment that had a different quality to it than the previous silences. There is no Vethkai word, they said slowly, for what you are describing. The closest translation would be denial of failure. I prefer fixing it, I said, but sure. I inventoried what I had. 3 sections of cargo bay sensor array housing aluminum composite, good thermal tolerance. 1 cracked communications relay with intact internal bracing. The relay was junk, but the bracing struts were a rigid titanium alloy. A tube of high-temp bonding compound I keep around specifically because deep space hates you and you should always have bonding compound. The plan was to build a crystalline brace, a structural sleeve that would hold the fracture faces in alignment and stop the lattice from flexing under resonance load. Not a fix exactly, more like a cast, like setting a broken bone so it can knit. I worked fast, hands moving on pure mechanics memory, cut the sensor housing to rough dimensions, stripped the bracing struts, test fit, measure twice, cut once more. Eichsthal stood in the hatchway and watched with the stillness of someone who cannot process what they are seeing but cannot look away. First attempt. I sleeved the brace around the lower third of the crystal, applied the bonding compound, and watched the plasma bleed at the fissure outlets drop from 17 sources to 4. Structural integrity climbed from 23% to 31%. Then the ship hummed. Not a good hum. A harmonic vibration, a standing wave building in the crystal lattice, resonating with the brace material at a frequency that was going to shatter the whole assembly if I didn't stop it in the next few minutes. I pulled my hand back from the crystal, checked my tablet. The vibration frequency was building logarithmically. I had maybe 40 minutes before it hit critical amplitude. New problem, I said. The crystal is failing faster, Eichsthal said. Something in their tone had changed, still flat, still translated, but there was a precision to it now. They were watching me the way a scientist watches an experiment. The crystal isn't failing faster, I said, already reaching back into my toolkit. The brace is resonating at the wrong frequency. The lattice is picking up the vibration and amplifying it, which means what I actually need to do is I stopped, thought, did the math in my head. That's interesting. What is interesting? I looked up at them. The resonance frequency of your drive crystal, do you know the exact value? Not the operating range, the fundamental natural frequency of the lattice itself. Another pause, longer this time. Eichsthal reached into a fold of their environmental suit and produced a small data chip, which they held out to me. I took it, plugged it into my tablet, read the number. Okay, I said. I've got 40 minutes and an interesting idea. You should probably stay close. I'm going to need your help with this. Eichsthal looked at me with their faceted eyes, catching the maintenance bay's light in small geometric flashes. You treat catastrophe, they said, as a puzzle. Is there another way to treat it? They didn't answer, but they stayed. 40 minutes to crystal catastrophe, and my best tool was a who kept telling me the math was impossible. I find that kind of motivating. Here's the thing about harmonic resonance, and I'm going to explain this the way my thermodynamics professor explained it to me, which is with a lot of hand-waving and a bad analogy involving wine glasses. If you tap a wine glass, it rings. It rings at its natural frequency, the frequency at which the glass wants to vibrate. If you hit it with a sound at that exact frequency, the glass will start vibrating harder and harder until it shatters. That's resonance. That's bad. But there's another option. You can damp the resonance, introduce a material that absorbs the vibrational energy before it can build. Or, and this was the interesting part, you can match the resonance. Create a second vibration at exactly the same frequency, precisely out of phase. The two waves cancel each other. The glass stops ringing. That's destructive interference, and it is one of my favorite things in physics. The brace material I'd used was resonating at a frequency close to the crystal's natural frequency, but not identical, close enough to excite the lattice, not close enough to cancel it. What I needed was a tuned dampener, something tuned to match the crystal's exact natural frequency and positioned to interfere destructively with the building vibration. My tablet showed me the target frequency. I needed something I could tune. I looked around the maintenance bay. Eichsthal watched me look. "What are you searching for?" they asked. "An oscillator, something I can adjust the resonant frequency of mechanically." I was already moving through the bay's equipment lockers. Ideally something small, rigid, adjustable. "There," Eichsthal said. I turned. They were pointing at a panel on the far bulkhead that I'd clocked as a calibration array when I came in. Vethkai design, dense with small crystalline components arranged in a geometric grid. "Station-keeping calibration nodes," Eichsthal said. "Each is a tunable resonance oscillator. We use them to calibrate drive harmonics during installation." I was already walking toward it. "Can I take 3 of them?" "They are components of a functioning system." "A functioning system that currently has bigger problems than its calibration nodes." I looked at Eichsthal. "Can I take 3 of them?" A pause, then, "Yes." I pulled them free, set them on the workbench, and started adjusting. Each node had a physical tuning mechanism, a compressed crystal element you could advance or retract to change the resonant frequency. I had the target number on my tablet. I started dialing. First attempt. I assembled the 3 nodes into a mounting bracket, tuned them to the target frequency, clamped the assembly to the crystal brace, and activated them. The vibration got louder for 3 seconds. Then I realized I'd oriented one node backwards. It was reinforcing the resonance rather than canceling it. I pulled it, flipped it, reclamped. I wrote down what I'd done wrong. Eichsthal watched me write it down. "Why do you record the failure?" they asked. "Because the next person who sees a broken Vethkai resonance crystal doesn't have to start from 0. I clicked my stylus. "Every wrong answer is a data point. Data points are how you find the right answer." Eichsthal was quiet for a moment. "Among my people, failed components are archived. The failure is cataloged and then the component is set aside. We do not build on failures." Seems like a waste. It is considered the correct response to finality. "Nothing's final until it actually stops," I said. "Hang on." Second attempt, node properly oriented. The vibration held for 6 seconds, then dropped. The harmonic amplitude began declining. I watched the numbers on my tablet fall, a slow, steady reduction as the destructive interference took hold. The crystal stopped vibrating. The maintenance bay went quiet. "There we go," I said. I ran the structural integrity check. 36%. Better than before. The plasma bleed was down to a single fissure outlet, a thin thread of vapor from a point near the crystal's upper edge. Eichsthal stepped forward and looked at the crystal, really looked at it, the way a doctor examines a patient, and said nothing for a long moment. "The failure has been paused," they said finally. The word they used wasn't quite paused. The translator gave it with a small asterisk indicating imprecise conversion. The Vethkai word was something closer to held at the edge of. "More than paused," I said. "But you're right that we're not done. 36% integrity won't survive a jump. Minimum threshold is 80%. I heard what that sounded like when I said it out loud. 36 to 80. A 44-point gap. No replacement crystal, no fabricator rated for Vethkai materials, and a ship that needed to be somewhere. So that's the new problem, I said. I sat down on the workbench, looked at the crystal and thought. Eichsthal sat down too. Not on the workbench, Vethkai don't sit in the human sense, but they folded into a lower stance, a change in geometry that I would later learn was the Vethkai position of engagement, of collaborative attention. Tell me, Eichsthal said, how you are thinking about this. I looked at them. You want to follow my reasoning. I have been watching you think since you boarded my vessel. I have never observed a pause, this process. Please, continue aloud. So I did. I talked through the problem the way I always do when I'm stuck out loud to whatever's listening because the act of putting it into words forces precision. The crystal lattice was fractured. The fracture had structural integrity of 36%. I needed 80. I couldn't add material to the crystal because I didn't have the right material and couldn't fabricate it. I couldn't replace it, so I had to work with what was there. Which means, I said slowly, following the logic, I need to make 36% of crystal do the work of 80% of crystal. That is not possible, Eichsthal said, not dismissively analytically. Not if the load is concentrated. But what if it isn't? I picked up my tablet, pulled up the crystal geometry data from Eichsthal's chip. The fracture runs diagonally. The stress during a jump concentrates at the fracture interface because that's where the lattice is weakest. But if I could redistribute the load, spread the jump stress across the intact portions of the lattice, rather than letting it all pile up at the fracture line. I stopped, did the math. Actually did the math, full equations right there on my tablet, Eichsthal watching every line. The numbers came back at me. "Huh," I said. "What?" "It works. If I redesign the mounting assembly, the bracket that holds the crystal in the drive housing, I can change the load distribution across the lattice. Instead of the jump stress hitting the crystal at its current contact points, which put maximum force right at the fracture line, I can shift the contact geometry so the force distributes across the intact upper and lateral sections." I showed Eichsthal the tablet. It's not adding integrity. It's moving the problem to where the crystal can handle it. Eichsthal looked at the equations for a long time. "You will need the original mounting schematics," they said. "Those are proprietary Vethkai engineering data." "I know." Another pause, shorter this time. Something had shifted in the last hour. I didn't call attention to it. "I will provide them," Eichsthal said. 61% integrity. Minimum jump threshold, 80%. The gap between those two numbers was my entire afternoon. Wait, I need to back up again, because I skipped something important. After the thermal refusion, which I'm getting to, I promise, the crystal landed at 61% structural integrity. Let me tell you how we got there, because that step matters. The fracture faces needed to be rejoined before the load redistribution could work. A fractured lattice with redistributed mounting still fails if the fracture itself propagates under jump stress. The force would just find the crack and finish the job. I needed the fracture faces to be, if not fully fused, at least mechanically bonded. Vethkai crystal expands when heated. Specifically, and this is in the data Eichsthal gave me, the lattice has an anisotropic thermal expansion coefficient, meaning it expands at different rates in different directions. Along the fracture face, high expansion rate, perpendicular to the fracture, low. Which meant that if I applied directed heat to the crystal along the fracture line, the crystal would try to expand in a direction it couldn't expand, the fracture face pressing against the other fracture face, and the lattice under that pressure might partially refuse. The math said somewhere between a 62% chance of partial refusion and a 23% chance of catastrophic propagation. Those are not comfortable odds. That's a 1 in 4 chance of shattering the crystal faster than the plasma bleed would have killed everyone. I did it anyway. My thermal probe heated the fracture line in 3 passes, slow and even, while Eichsthal stood very still, and I narrated every step to nobody in particular, which is a habit I have, and which I've decided is not weird, it's methodology. The crystal's internal structure showed up on my tablet as a color-mapped stress diagram, fracture faces glowing amber where the thermal pressure was building. At the end of the 3rd pass, the amber went white, and then the fracture line on my structural integrity scanner went from a hard edge to a soft gradient. 61%. Partial refusion, I said. Fracture faces have bonded at roughly 40% of contact surface. It's not pretty, but it's not going anywhere. Eichsthal was quiet again, with that particular quality of quiet. Now I had the mounting schematics. I spread them across the workbench, actual physical printouts, which Eichsthal produced from their data stores with a solemnity that told me this was not a trivial gesture, and started redesigning the bracket. The original mounting had 3 contact points: base, mid-lateral, and apex. Standard geometry for a symmetric load distribution. The problem was that it was designed for an intact crystal, so the load symmetry assumed uniform structural integrity throughout the lattice. My crystal had 61% integrity clustered in the upper 2/3, with the lower third still fragile despite the partial refusion. New design: 5 contact points distributed across the upper and midsections. Load-bearing geometry shifted upward and outward from the fracture zone. I was essentially asking the strong parts of the crystal to carry the whole jump stress, keeping the repaired fracture in a low-stress region during the transit. I built the new bracket from the station's titanium stock. I have a decent amount of it, structural grade, good yield strength. Cut it, drilled the contact point holes, test-fitted it against the crystal 3 times before I was satisfied with the geometry. Eichsthal handed me tools when I asked for them. At some point, they stopped needing to be told which tool I was asking for and started anticipating, reaching for the measuring caliper before I said the word, holding the bracket stable while I drilled without being asked. I didn't say anything about it, neither did they. Final test fit. Everything aligned. I installed the modified bracket in the drive housing, seated the crystal, torqued all 5 contact points to the values my revised stress calculations called for. Then I ran the pre-jump simulation on my tablet, a software model of the jump stress load, propagating through the modified mounting geometry. The numbers came back. Simulated integrity at peak jump stress, 83%. The fracture zone stayed below 15% of peak load. The intact lattice sections absorbed the rest. 83. Threshold was 80. Margin of 3%, which is, honestly, not a lot. I've worked with tighter margins and I've worked with worse outcomes. The math worked and the math doesn't lie, it just sometimes gives you answers that make your hands sweat. Simulation says 83% effective integrity under jump load, I told Eichsthal. 3% above threshold. I'd be happier with 10, but 3 will get you home. Eichsthal looked at the simulation results for a long time. Your species, they said, build stations whose entire purpose is to refuse to discard broken things. That's one way to put it. Among my people, a thing that is broken is finished. It is given respect for what it was and then it is set aside. Eichsthal looked at the crystal, sitting in its new bracket, refused and remounted and not, technically, by specification. We have not considered that broken might be a temporary condition. It usually is, I said. I picked up my wrench because I had nothing more profound to offer and also because I still needed to reseal the maintenance hatch. Nothing's finished until you say it is. Eichsthal left 2 hours later. The plasma trail was gone. The nacelles glowed clean, and even as the ship backed out of my dock and oriented for jump. I was halfway through logging the repair when the communication panel chimed. Eichsthel's voice came through, the translator working its careful standard. "Ruiz, we are ready to jump. I have one question before we go." "Sure. What do your people call a species that refuses to accept that something is over?" I thought about it. "Persistent," I said, "also occasionally annoying." A pause, then something that might have been a frequency change in Eichsthel's voice, something that the translator rendered as silence, but that landed differently than silence had before. The ship jumped, the dock was quiet. I finished the repair log, every step, every failure, every calculation, the thermal refusion odds, the mounting geometry derivation, the dampener tuning process, all of it. I put it in the Open Access Galactic Engineering Database under the tag Vethkai Drive Crystal Repair Field Expedient Method. Flagged it as preliminary. Noted that a sample size of 1 is not a study, but it's a data point. 3 weeks later, a Vethkai engineering vessel docked at Waystation Kaleo. The commander came through the airlock carrying a fractured resonance crystal and a data chip. "We read your database entry," the commander said. "Word travels fast." Vessel Commander Eichsthel transmitted it to the Vethkai Engineering Archive. A pause. "This is the first time a non-Vethkai methodology has been entered into our archive." I looked at the crystal they were holding. Different fracture geometry than the last one, perpendicular shear rather than diagonal, more fissures, worse shape overall. "And you've got a broken crystal." "We have questions," the commander said, "and a broken crystal." I reached out and took it. It was heavier than I expected, dense, cool, the lattice catching the dock lights in small violet refractions. "Then you've come to the right place," I said. I went to get my toolkit.